Okay, uh, today we'll be recording session 4B of our malware analysis lab, and um, we're going to be looking more at disassembly this time around, working with a 64-bit program. Um, and so we'll be in Binary Ninja, and the first part of the lab asks us how many arguments does create thread take. We're looking at this call to create thread here. Um, If I pull up the Microsoft documentation, we can see 1, 2, 3, 4, 5, 6 arguments. Um, and we can see it in the assembly here. Uh, 1, 2, 3, 4, 5, 6. Um, and it's asking uh, kind of our, I guess, what supports the conclusion here. Um, and we know with the 64-bit program that the uh, the RCX, RDX, R8, and R9 registers are used and for a call, and anything more than that needs to be pushed on the stack. Um, in our case here, we're talking about the 32-bit portion of those 64-bit registers, so that's why we see our EDX and ECX. But you could see these first four arguments here are those registers being populated, and then these final two up top are actually just pushes onto the stack. Um, so we're asked, how is the second argument passed to create thread? Second argument is an EDX, RDX register. Uh, so that's how it goes through there. Fifth argument we're asked about, which is this guy here, and that is an argument that's being pushed onto the stack. Then we're asked to jump to a function. So let's go to that function. And we are looking at a function where the program appears to interact with a service. Um, it then asks us to jump to this address and basically explain in plain language what's going on. So if we take a look at what this API function does, this registers a function to handle service control requests. It takes two arguments. It takes the service name and a handle to the function that will be handling those service control requests. And in the return, if the function succeeds, meaning that it's able to successfully register that function to handle service control requests, it will return a value that is the service status handle. If it fails, the return value is 0. Um, so we have our jump condition here, jump if not equal to 0. So what we can basically say, and we see that obviously the return value will be stored in RAX, and we see that being compared to 0 here. So what we can basically say is, if register service control handler W, which registers a function to handle service control request, fails, meaning it can't register a function, return 0. If successful, it's going to return that service status handle, which is a non-zero. And because our jump condition is doing a jump if not equal to 0, we're basically saying that jump if it successfully registers that function. Um, so um, that's what that says. And if we move to the next one, we're asked to go to another function. This one is doing some encryption. Same kind of thing, explain what's going on with the jump condition. And so I'll pull up that documentation, and this one, this crypt encrypt, it basically just it's a function that encrypts data. Similar kind of thing as the last one. If it succeeds, it's going to return a non-zero, and if it fails, it's going to return 0. So same kind of logic here. it's, we're checking to see if it returns 0, and it basically is going to jump if not equal to 0 to this address here. So the language we would say is if crypt encrypt fails, it returns 0. So basically, if it successfully encrypts something, then jump. But if it fails, then it won't jump. Um, right? Did I say that right? What's this? If the function fails, it returns 0. Yeah, okay. So if it fails, it'll return 0. And we're saying jump if not equal to 0. So yes, if it's successful, then jump. Okay. Then we're asked to go to this address here. And we're being asked, what does this instruction accomplish in the context of the code? So we're using load effective address here. And in the brackets here is this data variable. And because we're using load effective address, we don't really care what that value of that data, what that data is, the value of it. We care about the address of where that data variable is. So load effective address will grab the address of that data and put it into R8. Okay. And the reason we're doing that is because I actually didn't do this when I did it initially, but let me just look. So create mutex w, this is the third argument we're looking at, right? So the third argument, yes, so this is, so R8 will have the name of the um, the mutex object. Okay, and we can actually see that here. It looks like this is maybe the name of that mutex object. That's in this data variable, and that's at the address that's going to be an R8. Okay. Then we have to look at another function, this one here, and we're being asked what instructions form the prologue and what do they accomplish. So we're seeing shadow space here. We're basically seeing the values that are within EDX and ECX be dumped to the stack. And then after those registers are kind of emptied out, so we have their values on the stack, we're then creating that space on the stack by subtracting the stack pointer by 56 bytes. Then we're asked about the epilogue, and it should just be this instruction here, which is doing the cleanup of moving the stack pointer back up now 56 bytes and basically doing the opposite of what we were looking at here with the stack pointer. So that's the cleanup. And yeah, that's it. That's 4B. So thank you, Anuj.